Hello everyone, and today it's the fifth webinar for year 13 this year, and the topic is magnetic fields. I'm sorry, I'm a bit sick. I'm still trying to recover from last Saturday, and no luck. Anyways, when you study magnetic fields, it's really important to know vector product of vectors, so the cross product. So we can start with that. So the cross product of two vectors. So let's say we have vector A and vector B. The other way around. This is vector A and this is vector B. And the cross product is, so let's say that these two vectors lie in this plane. The cross product is a vector which is perpendicular to both vectors. So this is vector A times vector B. Now so that's let's label it C. The modulus of C is equal to the modulus of A multiplied by the modulus of B multiplied by sine of the angle between two vectors. So it's in a way similar to the oh, sorry. I should. In a way, it is similar to the scalar product, but instead of cos, you have sine. But of course, the big difference is that the cross product is a vector, whereas the scale dot product is a scalar. Okay, and the direction of C has to be such that if you are sitting on the tip of C, if you are sitting on the tip of C, this is not a very scientific definition. If you're sitting on the tip of C and looking down on the plane, So if you're sitting here, your eyes are down and you're looking downwards. So you're looking downwards. A must turn counterclockwise. The shortest way A should turn to B is anticlockwise. I don't know if that makes sense. Hopefully it does. So you can think of it, A and B are in the plane, and if you climb, C is like a column. If you climb on top of that column and you look down, and you look at you see two vectors A and B. So A must turn anticlockwise towards B. So that way, for me, it's that way. For you, might be different. So like this, and that's how you find the direction of C. Of course, there are different ways. There are other ways to find the direction of C, but that's the easiest definition to remember in my point of view. That's how I remembered it. Now, it also means that if you multiply cross B and A, if you find a vector B and A, they will turn the other way around. So B must turn to A counterclockwise. So C would be downwards. So the vector B times A would be in the opposite direction. So B times A. So B times A is minus A times B. And this property of the cross product is called anti-commutative. Commutative? Yes, anti-commutative. Anti-commutative. Whereas where A times B is obviously B times A for the dot product. So that's commutative. So you can switch them around and the product doesn't change. But with a vector product or the cross product, it's anti-commutative. So hopefully that makes sense. I need to switch on the chat if you have any questions. Okay. The easiest way to find the cross product of two vectors, if you have vector A with coordinates A1, A2, A3, and you have vector B with coordinates B1, B2, B3, then the cross product of A times B is the determinant of the matrix I, J, K, A1, A2, A3, B1, B2, B3. And if you don't know the determinant, please look it up. It's something you do need to know. And it's equal to the vector I multiplied by the determinant of A1, A2, A3, B2, B3, minus J multiplied by the determinant of A1, A3, B1, B3, plus K multiplied by the determinant of A1, A2, B1, B2. And of course, this can be simplified as A2, B3 minus A3, B2 multiplied by vector I minus A1, B3 minus A3, B1 multiplied by vector J plus A1, B2 minus A2, B1 multiplied by vector K. It looks complicated, actually. Definitely isn't, as we will see in a minute. Okay, so we have two vectors A and B, and we need to compute the vector C, which is A times B. These are obviously vectors, so let's do that. So C, or let's say A times B, C equals A times B is the determinant of I, J, K. Then 2 minus 1, 4, 3, 5, negative 2. That's equal to 2 minus 20 multiplied by I minus 2 minus 12 multiplied by J plus 10 plus 3 multiplied by K. Does everyone understand what I just did? Please let me know. Thank you. All right. And Ines, I know you just joined, but what do you think? Not quite. Do you know how to find the determinant of a 2 by 2 matrix? Okay, so what I did is, so I found that I need to find the determinant of a 3 by 3 matrix. And to do this, I take the first element and I multiply it by the determinant of this 2 by 2. The determinant of this 2 by 2 is 2 minus 20. Then I do minus the second vector multiplied by the determinant of this matrix of 2, 4, 3, minus 2. So that's that's minus 4. Sorry, minus 4, minus 12. And then finally, I do k multiplied by the determinant of this small matrix. Okay, does that clarify things? Okay. All right. So, and now I'm finding the cross product of two vectors. And finally, I get minus 18i, 16, so minus 6 plus 16j plus 13k. I don't know about you, but I hate base vectors. I much prefer columns 16, 13. Okay. It's just visually very noisy too, but that's me. 18, 16, and 13, and then verify that they are perpendicular. So that's question A. So what I do is I multiply C times vector A, and that is C, which is minus 18, 16, 13, multiplied by A, which is 2 minus 1, 4, which is negative 36, negative 16, plus 52, and that is 0. Hence, uh, hence C is perpendicular to A because their dot product is 0. And similarly, C times B is equal to minus 18, 16, 13, multiplied by B, which is 3, 5, negative 2, which is negative 54, plus 80, minus 26, which is also 0. Hence, C is perpendicular to vector B. And B, find the magnitude of C at the angle between A and B. The magnitude of C is simply the square root. 16 squared plus 13 squared. 18 squared plus 16 squared plus 13 squared. That's 7, square root of 749. 49. And the angle between A and B, so we know that the cosine of the angle is A times B divided by modulus A multiplied by modulus B. And that's equal to A times B, which is 6 minus 5 minus 8 divided by modulus of A, which is 4 plus 1 plus 16, 21. And B is 9 plus 25 plus 4, 38 times 21, 79. Oh, that's really annoying. Is it? 21 times 38, 798. That is super. Oh no, that's fine. Okay, so 1 minus 7 over root 798. and then we need the angle. Well, it's our cos of that. I don't know if we actually need to calculate the angle. So the angle, okay, let's do the angle. AB is arc cos of -7/798, which is cos of -7 divided by √8. Ooh. Divided by pi multiplied by 180. 104 degrees, 104 degrees, approximately, of course. Angle and right. One more thing that I forgot to mention. One more important thing that numerically, let's label it properties. Properties. So how to find, and then another property. If you take vector A and vector B, then the cross product is equal to the area of a parallelogram drawn. So the cross product A times B modulus is equal to the area of parallelogram. And that's easy to prove because if this angle is theta, and remember we just said that A cross B is equal to modulus A modulus B multiplied by sine theta, which is the area of a parallelogram. Okay, nice. Oh, cool. Moving on. A proton with charge E moves at a speed perpendicular to a magnetic field. So we have a magnetic field. Let's say magnetic field is into the page. It doesn't matter which way it is. And a proton is moving with velocity v, and it has charge q and mass m. Find the radius of its circular path. Well, the path of the proton is going to be circular, and the proof of that is in the assignment. I have also done several webinars on this topic, so you can always go back and see the previous webinars. They are slightly harder, so today is a slightly easier webinar. And we know that we can use the left-hand rule. So the current is along the velocity, so current is down. Field is into the page, so there will be a force to the right. So the proton will be deflected to the right or to the left if you are the proton, and the radius will be r. And at any point in the trajectory, the velocity is this, and the force is towards the center. And we know that the force is QVB. But we also know that it is the centripetal force, therefore it is also equal to mv squared over r. And here we get that r is equal to mv squared divided by qvb. V cancels, and it's equal to mv divided by qb. So the radius of the path is equal to the momentum of the particle divided by Q times B. That's very useful. And that's, we need the mass of the proton. We know that the mass of the proton is 1.67 times 10 to the minus 27 kilograms. And we can calculate the radius. Mass 1.67 times 10 to the minus 27 kilograms multiplied by the velocity 4 times 10 to the 6 meters per second divided by Q, which is 1.6 times 10 to the minus 19 multiplied by 0.25 Tesla. And that's coulombs, Tesla, and we get something. 1.67, 10 to the minus 27. Negative 27 times 4, 10 to the 6, 1.6, 10 to the minus 19, 0.167 meters, which is 16.7 centimeters. That's very reasonable. And then determine the time it takes to complete one full revolution. B. The time it takes for one revolution. So the time period is equal to the distance traveled, 2 pi r, divided by the speed, v, and that's equal to 2 pi times 0.167 divided by 4 times 10 to the 6 meters per second. This is meters. And 2 pi times answer divided by 6. 2.62 times 10 to the minus 7 seconds. And we can also do the cyclotron frequency. The cyclotron frequency is the how many rotations it does per second. So cyclotron frequency. So a cyclotron is a device that causes electrons to move in circles, right? And the frequency will be 1 divided by time period, and that is 1 over 2.62 times 10 to the minus 7, which is 3.81 times 10 to the 6 hertz. So 3.8 megahertz. Nice. A radio frequency. 3. A beam of singly ionized neon ions enters a region with magnetic field. Accelerating voltage is there. Find the radius of the curvature of the ions in the field. So it's a very similar question, except we don't need to know the speed. We need to work it out. So what is accelerating voltage? Accelerating voltage, so means that there's two plates, or a plate and a net. Okay. And there is a potential difference of 1.2 kilovolts. So a neon ion, let's say it originates here. So it's a neon plus. And because this plate is positively charged, it accelerates away from the positively charged plate towards the negatively charged mesh. I want to say mesh. It accelerates. And then when it exits the It has a speed. We don't know what speed it has, but we do know that the kinetic energy is equal to the charge multiplied by the potential difference, charge by voltage, Q times V. And that is, in fact, 1.2 kilo electron volts. The kinetic energy of the ions will be 1.2 kilo electron volts. We can convert that to, because the charge is 1 electron. So how did I arrive here? I'll just quickly explain. Because I know the voltage is 1,200 volts, or 1.2 kilovolts, and Q is equal to E. So I literally just substitute that in. So E multiplied by 1.2 kilovolts, which is equal to 1.2 kilo electron volts. Cool. And then I know the speed of the particle. I can find the speed of the particle because I can convert this into joules. The 1.2 K multiplied by 1.6 times 10 to the minus 19 joules, which is 1.2 times 1.6 times 10 to the minus 16 is 1.92 times 10 to the minus 16 joules. That's the kinetic energy of the ions. And then we can work out the speed. Speed is equal to double the kinetic energy divided by the mass square root. So 2 times 1.92 times 10 to the minus 16 divided by the mass, 3.35 times 10 to the negative 26 kilograms. This is joules. And I get square root of 2 times answer divided by 3.35 times 10 to the negative 26. 1.1 times 10 to the 5 meters per second. And because they enter, once these ions are accelerated by the accelerating potential, when these ions are accelerating potential, they enter a magnetic field. Let's say they enter the magnetic field, which is at right angles to that. Now they enter the magnetic field. So the magnetic field is into the page. So the force is going to be upwards. So they will be deflected upwards. And we need the radius. And we already know that the radius is mv divided by bq. And all we need is 3.35 times 10 to the negative 26 times 1.1 10 to the 5. That's the speed divided by 0.4 Tesla times Q, which is the charge, was 1.6 times 10 to the minus 19 coulombs. This is meters per second, and this is kilograms. And we get something. Answer times 3.35 times 10 to the negative 26 divided by 1.6 times 10 to the minus 19. And we get 0.056 meters. Cool. Which is about 5.6 centimeters. Lovely. Okay, moving on. This is getting more interesting. A charged particle of mass m and charge q enters a region with both an electric field and a magnetic field, find the velocity of the particle, find the velocity with which the particle moves undeflected. So there's a situation that a magnetic field, there is a magnetic field and an electric field. The magnetic field pushes the particle one way. The electric field pushes it in another way. And if it says that they are the particle moves undeflected, that simply means that the total force is zero. Are you familiar with the velocity selector? Do you know what a velocity selector is? Please let me know in the chat. Okay. Let me just briefly explain what a velocity selector is. Velocity selector. So, imagine you need a device that accelerates particles, but it accelerates particles to the exact speed you need, and the mass of the particle does not matter. It would be amazing, right? It would be amazing if we had such a device. Okay, so what we do, we accelerate particles using an electric field. That's easy. So we have two plates, a positive and a negative, and we inject a positive particle here, and it will escape, it will accelerate away from the positive towards the negative through the holes, and it will emerge from this end. Now, the problem is that not all particles will have the same speed. So because some of them start from different points in the fields, some of them bump into the net or something else. So you want something here that is called a velocity selector. Velocity selector. Basically, it's a filter that if you have a fixed velocity that we need, it goes through. And if it doesn't have that exact velocity, it is stopped. Okay. So how does the velocity selector work? So only particles with exact speed can pass. Okay. So it's like I don't know. A velocity selector works in the following way. Velocity selector. It has a magnetic field inside. And if a particle is traveling to the right with velocity v, that causes, so boom, boom, it causes a magnetic force upwards. Magnetic force. I hope you understand that. Yeah? Does everyone understand? If the particle is moving through a magnetic field, it has a charge Q, it will be deflected upwards. Okay. What we do now is we place an electric field which is perpendicular to the original one. So we place two parallel plates, positive on top and negative on the bottom. And there's an electric field going downwards. So the particle also experiences an electric force going downwards. Electric force. And the particles, if magnetic force is equal to electric force, particle goes in a straight line. Goes in a straight line. And let's look at the conditions. So the magnetic force equal to the electric force. We know that the magnetic force is QVB, and the electric force is QE. Q cancels. Like, blimey, Q cancels. We don't even care about the charge of the particle. And then V is equal to E divided by B. Both E and B can be adjusted to select the necessary speed. So if the particle moves too fast, the magnetic force will be bigger. And oh yes, and at the end we place a tiny window on the other side. Small window. Small window. So if a particle has exact velocity, it goes through the window. Speed is exactly E divided by B. If it's too fast, it will be deflected upwards because the magnetic force will be bigger. Too fast. And if it's too slow, it will be deflected downwards and it will hit this barrier. Too slow. So that's how a velocity selector works. So if a particle is too fast, it hits the wall. If it's too slow, it hits the other wall. And if it's just right, it is allowed to pass through. Okay. On a scale of 0 to 10, how well do you understand the velocity selector now? Okay. A velocity selector is used in mass spectrometry. So if you read about mass spectrometry, is a really cool stuff. It allows you to find the masses of atoms correct to 10 to the minus 32 kilograms. Something astonishingly good accuracy. Yeah, so it can actually weigh atoms. It can tell the difference between a uranium-232, sorry, a uranium-235 and a uranium-236. It's that accurate. Can you imagine? So 0.2%, 0.5% of a single atom, which is quite cool. Anyways. Now, a charged particle of mass, and it is so basically what that means, because this is a slightly formal problem, we know that the electric force must equal plus the magnetic force must equal to 0. And the electric force, we know that the electric force is the charge multiplied by the electric field plus the charge multiplied by the velocity. Ooh, which way around it is? I always forget. Is it VB or BV? I think it's VB. QVB, yes. QV times B, and this is a cross product. And that's equal to 0. Now, Q is a scalar, so we can divide by Q. So that doesn't matter. And we have the electric field, which is 0, 100, 0, plus. Now, V is, well, V, cross product, B, which is 0, 0, 0.5. And that's equal to 0. To solve this, I'm looking for V. So to solve this, there's no vector division. not that I'm aware of any vector division. What I'm going to do is I'm going to write V. Uh, V is Vx, Vy, Vz. So it's the velocity in the x direction, velocity in the y direction, velocity in the z direction. And I'm going to multiply these two vectors together. So Vx, Vy, Vz cross 0, 0, 0.5, which is, so this is V times B, and that's equal to Ijk Vx, Vy, Vz, 0, 0, 0.5, open brackets. So I multiplied by 0.5 Vy minus J multiplied by 0.5 Vx plus K multiplied by 0. So the product is 0.5 Vy minus 0.5 Vx and 0. This is the cross product of V and B, and we substitute that back into our equation. So 0, 100, 0 plus 0.5 Vy minus 0.5 Vx and 0, and that's equal to 0. Hence, Vy must equal to 0. Vz can be anything, by the way. Oh, wow. Vz. We don't know anything about Vz. Vz, yeah. So Vx is, as you can see, it's 200. If you solve this equation, 100, 100 plus minus 0.5 Vx is 0. So Vx is 200 meters per second. And Vz, it could be anything. So we could say, could just say it's 0. Why not? The simplest. Find the smallest velocity v which the particle moves and deflects through the region. Okay, I'm a bit cheating here. I don't want to go too deep into that. So yeah, and then so I finally got the velocity. I got the velocity which is 0, sorry, 200, 0, 0 meters per second. So only particles with this velocity are allowed to pass through, which is very nice. And what else can I say here? Well, if you draw this in 3D, it also makes perfect sense. I'll leave that exercise to you. Question 5, a rectangular loop. Okay, a rectangular loop of wire, size 10 centimeters and 5 centimeters, carries a current of 2 amps. It is placed in a uniform magnetic field, such as the plane of the loop makes an angle of 30 degrees with the field direction. Find the torque in the loop. Okay. They don't specify how the loop is oriented. Is it oriented like this or like this? Why does it make a difference? Because the angle could be this way, like it can be tilted this way, or it could be tilted this way. So because it's not specified, we're going to do both. Okay, tilted this way or tilted this way. Okay. So it's in 3D. It's a bit annoying. So imagine you have a loop. Uh, I'm so bad at this. Drawing loops in 3D is kills me. Okay, so let's have a magnetic field here, and we're going side view. So we place the loop like this. So we have a rectangular loop A, B, C, D, and L is 10 centimeters, and this is 5 centimeters. So let's say that this is the longest side. So this is BC, and A is behind B, and D is behind C. So we're looking at the side view. And we know that the angle between the field and the loop is 30 degrees. Okay. So we need the force experienced by the wire CD. So CD is a section of wire, and let's say the current flows from C to D and from A to B. So in this picture, the current flows into the page, and here the current is flowing out of the page. Right. So force on the section CD of the wire. So this section CD, it's here. It experiences a force. So field current force. So it's a downwards force, FCD. And FCD is equal to BIL, which is equal to 0.8 Tesla times current, which is 2 amps, multiplied by the length, which is 0.05 meters. And the torque is, so and that's the force. So 0.8 times 2 times 0.05. So 0.08. 8 newtons. That's the force. So that's 0.08 newtons. Similarly, this force is also 0.08 newtons. The torque is the moment, and it's the moment about the center. Let's call it point O. It causes a clockwise moment. So this magnetic field will cause the coil to turn clockwise, and we have the moment. So force on AB is also 0.08 newtons. Okay, so the moment, well, it's in our case, CD is perpendicular to the field. Yes, CD is perpendicular to the field, so theta is 90 degrees. So we don't need sine theta. Okay, so the moment is this is the distance. So this is the perpendicular distance to the pivot. So this is 5 centimeters. 5 centimeters times cos 30. So moment is 0.05 times cos 30 degrees, multiplied by the force, 0.08, and multiplied by 2 because it's twice the moment, right? We have two moments in the same direction. So 0.05 times 0.08 times 2 times cos 30. So pi over 6. Calculate it in radians for some reason. So it's 0.0069 Newton meters. It's a very small moment. Have I made a mistake? No, I don't think so. No, it's a small distance and a small force. 0.8 times 2. Yeah, okay. Now, the moment would be maximized if BC was horizontal. If BC is horizontal, then so when O is here, this is C, and this is B. Now, the force is downwards and force is upwards. So the difference would be that the angle is 0 degrees. So moment is 0.05 times cos 0 degrees times 0.08 times 2. And that would be 0.05 times 0.08, 0.008 Newton meters. Now, I haven't done the calculation, but I believe if we change the orientation of the coil, the answer would not change. Let me check. So if we placed the short end of the coil like this, so if this is 5 centimeters, so this side is AB, so this is A and this is B. And we are looking at the force on the section BC, so FBC, and force on AD, And the force on the section BC is the same as the force on the section AD, which is equal to the length, so BIL. So what's B? B is 0.8 multiplied by 0.1. That's the current is 2 times, and the length is 0.1. 0.8 times 2 times 0.1. That is 0.16. 16 newtons. So it's double the force, but because the distance is shorter, the length is shorter. So the moment is 2 times, and it's still 30 degrees, 2 times 2 times the force times the distance, which is 2 times 0.16 times 0.025 times cos 30 degrees. And I believe that 2 times answer times 0.025 times cos I over 6 is the same, 0.00693 Newton meters. And the maximum max would also be 0.008 Newton meters. So it doesn't matter. It doesn't matter which way you have the coil. Is it like this or like this? Meaning the moment in that direction would be the same as the moment in that direction. I don't know if that's because the ratio is 2 to 1 of the coil. Maybe it is, maybe it's not. And maybe you can check it out. Okay, we've got 3 more questions. 2 long parallel wires are separated by a distance of 20 centimeters. So I've got a formula here, which I will use. I've done the proof of that formula last year. So if you want to watch last year's webinar, there's a proof of this formula. 2 long parallel wires are separated by a distance of 20 centimeters. Wire 1 carries current of 5A, and wire 2 carries a current of 8A in the opposite direction. So I'm going to draw the first wire like this, and wire 1 carries a current of 5 amps into the page, and the other wire is carrying a current of 8 amps out of the page, and they're separated by 20 centimeters. Now, the first wire produces a magnetic field around it, and it's in that direction. And that means in the position of the second wire, that magnetic field is downwards. So the magnetic field for this wire, as far as this wire is concerned, the magnetic field is downwards. So the magnetic field of the first wire is downwards at the point where the second wire is located. Now, for the second wire, you can find the force. The force, so the magnetic field is down. Current is out of the page. So the force is this way. Now, if you do a similar argument, well, you can just do Newton's third law argument. If wire 1 pushes wire 2 to the right, then wire 2 pushes wire 1 to the left. So it is a repulsive force. Nice. Okay. Find the magnetic field at a point halfway between the wires. Oh. So find the magnetic field here. Halfway. So we know the magnetic field of the first wire is downwards, B1. And the magnetic field of the second wire is upwards, and that's B2. Oh, it's not. It's in the same direction, sorry, because it's anti-clockwise. So it's, yes, using the right-hand rule. So B2 is also downwards. And we know that B1 is equal to mu0 I1 divided by 2 pi the R1, and B2 is equal to mu0 I2 2 pi R1. So B total is equal to mu0 divided by 2 pi R divided by, well, R is half the distance. 2 pi R multiplied, so, or I1 plus I2. Oh, that's quite, yeah. So that's the magnetic field. You can substitute the numbers, but that's not important. R is, in this case, is 10 centimeters. Determine the force per unit length on each wire. State whether the force is attractive or repulsive. So B, force is repulsive. And the force is equal to BIL. So if you take the second wire, we need it's B1 multiplied by I1, or I2, sorry, the current in the second wire. So I1 is this is I2. So the field of the first wire times the current in the second wire times the length of the second wire. And we know that's equal to mu 0 I1 divided by 2 pi d, the distance, multiplied by I2 and multiplied by the length of the wire. And force per unit length is equal to mu 0 I1 I2 divided by 2 pi d. Where's the distance between the wires? Quite a useful formula. It's force per unit length. And recall force between two charged particles is Q1, Q2 divided by d squared. Somewhat similar. Not the same, of course, but somewhat similar. Okay, number 7. A circular loop of radius 0.1 carries a steady current of 3 amps. So we have a loop of wire, and the current in that loop is 3 amps. And we know, well, we've proved that in the assignment. Again, I did that proof in one of my previous webinars, or it's in the assignment, so that the magnetic field at the center of the loop is this, mu 0 I divided by 2R. So A, the magnetic field at the center of the loop is mu 0 I divided by 2R. Okay, let's do the calculation. Mu 0 is a constant. Magnetic permittivity of free space, and it's a constant, number 33, multiplied by current, which is 3, divided by 2, and divided by 0.1, which is 1.88 times 10 to the minus 5 Tesla. That's about the same as the magnetic field of the planet Earth. So the magnetic field of the Earth is about this much. B, determine how the field changes if the loop is made 200 turns without changing its radius. Well, each loop has its own field. So if you have 2 loops, you double the field because the field adds up. So B is going to be 200 times B of a single loop, which is simply times 200, which is 3.77 times 10 to the minus 3 Tesla. That's why we tend to have multiple coils of wires. Okay, so I hope that makes sense. Sorry, I know I'm not doing any integrations today. Partly because I've done so many in the previous sessions. I wanted this to be a simpler approach. But yes, you're welcome to explore how the integration is done. A uniformly charged ring of radius A carries a total charge Q. So this is similar to the last question in the assignment. If you look at the last question in the assignment, it's pretty much the same. Oh, it's similar. A thin uniformly charged disk of radius A and total charge Q spins with angular velocity. What's the magnetic field at the center of the disk? So a thin disk is just many rings put together, right? So it's multiple rings. Now we're doing a single ring and uniformly charged ring. So we have a ring which is charged. Let's say it's positively charged. It doesn't really matter how it is charged. But when positive charge moves in a circle, that's electric current. So as the charges move in a circle, that's electric current. So current is charge divided by time, and the total charge is Q. And in the time it takes for one rotation, time for one rotation, uh, is time period, which is equal to 2 pi divided by omega. Therefore, it's Q divided by the time period, which is Q divided by 2 pi times omega, which in other words, Q omega divided by 2 pi. That's the current due to the ring spinning. If you think of the ring spinning, it's is the ring is charged, produces a current. Now, if I do the second part, find the magnetic field at the center of the ring. But now it just becomes really basic because we know that the magnetic field at the center of the ring is equal to mu 0 I divided by 2r, mu 0 I divided by 2r, and what do we know? We need the current. So it's equal to mu 0 multiplied by q omega divided by 4 pi r. And that's the magnetic field. And now, to do problem 11, you can think of the disk is made up of multiple rings. Charge on each ring is proportional to the radius. The magnetic field of each ring is Bi equals mu 0 Qi omega divided by 4 pi Ri, where Qi is the charge, Ri is the, oh, nice. Because Q is proportional to R, they kind of cancel out in a way. Ri is the radius. It's charge of ring I, radius of ring I, and yeah, the total field B total is just the sum of BI's from all the rings. And of course, you don't normally do sums, you do integrals. So B total is going to be the integral of this thing, mu 0 Qi omega divided by 4 pi Ri. You'll need the width of dr. I'm not 100% sure about the dr, so I'll leave it to you. I'll leave it to you to figure it out. So something in that regard. So hopefully that helps with problem 11. And yeah, so I hope that was useful. And I'm going to stop here. I'm going to go and try to get better. Try to fix my cold and yeah. Enjoy doing the assignment. I think it's one of my favorite assignments yeah, at Compos, probably after circular motion, but yeah. All right. Enjoy and see you all in 2 weeks' time, I think. Yeah, 2 weeks' time. Welcome.